Lecture 20, Part 1. This is the last lecture that's relevant to the final exam. So I will record Lecture 13 and Lecture 21, but they will not be relevant to the final exam, not relevant to all the homeworks. So Lecture 20 is basically the last one that's related to the course material that will be tested. And we'll continue and finish game theory. And in the previous lecture, we talked about sequential games. We actually never used the name, but the games that we talked about are sequential games, and this time we will be focusing on simultaneous move games. So what I mean by sequential games is that one player would make an action, would choose an action first, and then the next player will choose another action, given the action chosen by the previous player, and then the next player will choose another action, and so on. And here, when we're talking about simultaneous move game, as the name suggests, all the players are moving at the same time. So technically, it's not really necessary that they move at exactly the same time. It's just the main point is that when everyone is making a choice, they do not know the choices of the other player. So if the game has a structure like that, then we're calling it a simultaneous move game. So the example that I'm going to use is the guess 2/3 of the average game that I remember mentioning it at the beginning of the summer, but let me repeat the rule of the game. So we can have arbitrary number of players, and each player is writing down an integer between 0 and 100. And the goal of the game is to get a number that's as close as possible to 2/3 of the average of everyone else's number. So to solve this game, we cannot say that we want to solve the last player strategy and then go back to the second last player, because they are making the choice at the same time. So at least when the last player is making a choice, he or she does not know anyone else's number. So we need to somehow figure out the solution for all the players at the same time. So let's start this by writing down the possible actions. And I'll call the set of possible actions R0. 0, 1, 2 until 100. So these are all the possible actions. And let's look at maybe the action 100. Would 100 be the best action in any case? So imagine if everyone else is picking 100. Then 2/3 of the average is 66. So maybe choosing 66 or 67, those two numbers may be reasonable. But it's actually never possible that 2/3 of the average is closer to 100 compared to 66 or 67, no matter what the other players are doing. So basically, 100 is never a best choice. So technically, we will use the term strictly dominated, but I will talk about that in the next part of the lecture. But here, let's just get rid of all of those actions that are never good. And that include 100 and 99 too. 99 is actually never better compared to 66 or 67 at least. So anything larger than 67 actually is not good. So we can write 66 if we want, and 66 is a nicer number, so let's just write 66. 67 is okay too, because yes, in the worst case, if everyone else is picking 100, then yes, it may be 67 is better than 66, but it's a small technicality. Now we know that everyone should be thinking like this. So everyone should think that they should never pick anything larger than 66. So essentially, we are switching to the other game that says we are picking numbers between 0 and 66. And we can apply the same logic, and we can get to 44. Because any number larger than 44 will not be closer to whatever 2/3 of the average is compared to 44. So again, technically it's called 44, it strictly dominates all of the other actions. So we can remove all of these dominated actions because they will never be chosen. They should never be chosen by a rational player. And but by the way, the R here stands for rationalizability. And then we can continue the process. And what's 2/3 of 44? I remember 29 point something, so let's try 30 here because it's a nicer number again. And we can basically apply the same logic and get it down to 20. And you can probably guess what I want to do. Repeat this infinite number of times. Actually, finite number of times is okay, but let's say infinite times. Then we can get it down to 0 and 1. So let's actually think about, can we get rid of 1? If everyone else is picking 1, then 2/3 of the average is around 0.6, which is closer to 1 compared to 0. So no, we cannot actually get rid of 1. Sometimes when 1 is good, 1 is better than 0. Sometimes 0 is better than 1. So we cannot get rid of any of these. So we're going to call the remaining set the set of rationalizable actions. And we're going to use this as our first solution concept. So basically, when we see a simultaneous move game, we can say that the rationalizable set of actions is kind of like the solution, the possible solutions of the game. And here it is everyone should be picking either 0 or 1. So we didn't narrow it down to everyone must pick 0, everyone must pick 1, but we narrow down the set of actions, so it's kind of reasonable and it's kind of what we want to do. But there are two main problems with this. First is when people actually play this game, they don't just pick 0 and 1. So on my website, I actually have the link to a game that was played a long time ago with a lot of players, and I think they are picking numbers between 0 and 1,000 million or something, but let's just say they are picking numbers between 0 and 1,000. And indeed, many people are picking numbers between 0 and 100 here. Actually, majority of the players are picking those numbers. So using our scale, it means majority of the players are picking numbers between 0 and 10. And actually, not many people are picking numbers between 30 and 100. So it's kind of people are rational, but people are not that rational. And it's not even that case. So to actually think about this, so there are people, of course, there are people who are just picking random numbers. So they may pick something like 500, 600 or something like that. That's completely irrational. And even if I'm rational, I may not want to assume everyone else is rational. So if I'm just assuming I'm rational, but I'm assuming everyone else is irrational, then I would say everyone else is just picking a random number, then the average is around 50, and 2/3 of 50 is like something between 10 and 20. So I guess many of these people, they are assuming that. They're assuming other people are picking randomly, and I'm just being rational. And there, of course, there will be other people who are assuming other people are assuming this, and then I'm just one level more rational than the other people. So well, it's not really strictly about rationality. It's also about whether I believe other players rational, whether I believe other player believe that I'm rational, and whether I'm believing other players believe that I believe that they are rational, and so on. So basically, there are lots of levels to consider. So I will actually put this question in M12. So you have to pick a number as well. So your number should not reflect your rationality. So I'm not asking everyone to pick 0 or 1. I'm asking everyone to think how many other students are actually paying attention in this class, how many other students are rational, and how many other students are thinking that you think that they are rational, and so on. So we will actually try this, and I will post the result after the due date of M12. Okay, let's get back. to the mathematics. So the problem with rationalizable actions that we actually care about in game theory is that for most of the games, the set is too large. So here, the set is kind of small. So we reduce the set of 100 numbers, 101 numbers to 2 numbers. So it's kind of reasonable. But for most of the games, the set of rationalizable actions is just the set of all possible actions. So basically, we didn't do anything. So that's why we need some kind of refinement to this solution concept. We need a better solution that's actually just a single prediction of what will happen, and that will be our Nash equilibrium. But before I move on to that, in the next part of the lecture, I want to first talk about rationalizability. And in the previous semester, some of these professors who taught 540 call rationalizability as the solution of iterative elimination of strictly dominated strategies. So iterative elimination of strictly dominated strategies. So they are exactly the same thing. So what I mean by rationalizable set is the same set. So in M12, I actually use this term instead of rationalizability. So the idea is the same. Is we start with one rationalizable, which means we are removing the strictly dominated actions, and that set is roughly the same as the actions that are never best responses. There are some technicalities, but I'm not going to mention it here. But basically, we are removing the actions that are never good. So that's one rationalizable. And if we repeat on the game with those actions removed, and then it's called two rationalizable. And then basically, if we keep doing this, and that's why it's called iterative elimination. If we keep doing that infinite number of times, usually for at least for the questions on the homework and exams, there will be finite number of iterations, and then you will stop, and then the remaining set of actions, I will call it the set of rationalizable actions.